These next two videos are going to cover two more geometry topics. Today, or in this lesson, this video will be finding the length of a curved function, and then the next video will be finding the surface area of those three-dimensional objects we've been finding by rotating around an axis. We've been finding the volume. In the next video, we'll find the surface area. But in this one, we're going to talk about arc length. So we're going to look at how long a curved surface is. If you were to walk across the St. Louis Arch, for example, from the bottom all the way across the top and back over, how many feet, miles would you walk? So we want to find the length. So I'm going to show you an example here. This is a generic example, and we're going to use the idea that we've been using for a lot of this geometry. We're going to find one small thing and then integrate to do that an infinite number of times. For an area under a curve, we found the area of a rectangle under a curve. For volume, we looked at the volume of a cylinder and then did that an infinite number of times or integrated that. So we're going to do the same thing for this arc length. We're going to pick 2 points. So what we're trying to find is the length of the arc from A to B. So we're going to pick 2 points, just 2 representative points. It doesn't matter where. I'm just going to choose this as C right here, and this one will be D. And I'm going to find the distance between those 2 points. So this is F of C and F of D. If I can find the distance between those 2 points and assume that they're infinitely close to each other, but I made them a little farther apart for this image so it's easier to work with. But imagine those 2 points are infinitely close. I'm going to find the distance between those two. And this distance just comes from something you've been doing most of your mathematical life, or at least since middle school, and that's use the Pythagorean theorem. So if I draw a right triangle in here, I know that the hypotenuse of that right triangle is the distance between F of C and F of D. So that would be the length of that part of the arc. All right, so I know that C and D are infinitely close, so I'm going to call this length some small change in x. I'm going to call that dx. And the height of the triangle is some small change in y, so I'll call that dy. So in order to find the length of that small tiny arc from f of c to f of d, I'll just use the Pythagorean theorem. So from f of c to f of d, the distance is the square root of dx squared plus dy squared. So if I just find an infinite number of hypotenuses from A to B, that'll give me the length of that arc. And we know that integration really helps a lot with that because integration is accumulating those values over time. And I'm going to find the antiderivative or the integral from A to B. It's going to accumulate all of those little segments. But the way we've written this integral is not proper because an integral must be some function and then a dx, some kind of change in x. Well, I see that we have a change in x under the radical, so let's do a little bit of algebra here. So the algebra is going to get a little bit tricky, but not in a bad way. It's just different. Once you've seen it once, it will make more sense. What I'm going to do is rewrite my dy squared. I'm going to introduce a fancy form of 1. I'm going to multiply dy squared times this fancy form of 1. dx squared over dx squared. And there's a method to the madness, and just bear with me for right now, because what I can do then is rearrange this, that second term there, and I'm going to rewrite that one now. Hold on, sorry. I'm going to rewrite this as dy squared over the bottom dx squared, and then I'll still have this dx squared left over. The reason I did that now is that I see that both terms, this term and this term, both have a dx squared in common. So I can factor out a dx squared. Now everything I'm doing never needs to be done again. I'm just deriving this formula for you. I'm just showing you where the equation for arc length comes from. You'll never have to reproduce this ever, but it's interesting to see where it comes from. All right, so if I factor out a dx squared, I end up with 1 plus dy squared over dx squared. The nice part about radicals is when I have two things being multiplied together under a radical, I can write them under their own radical. So for example, I can write this as the square root of dx squared times the square root of 1 plus, and I'm going to rewrite that dy squared over dx squared. I'm going to write it as dy over dx, the whole thing squared, because dy over dx is something that we recognize. All right, now we're getting to a form where we can start to use this. I know that the square root of dx squared is just dx, so I'm going to put that dx outside at the end because that's where we're used to seeing it. And then that radical, the square root of 1 plus dy over dx, well, we know that dy over dx is a formal way of saying the derivative. So this is 1 plus the derivative squared. This is how we find the length of an arc for any curve. So that's how we find the length of the arc from A to B under the function, or of the function f of x. It's 1 plus the derivative of the function squared. Now, like I said, all that I just did was just deriving this formula, just creating it so you see where it comes from. But now let's actually use it. So I'm going to give you a function. We'll do two examples in this video. Find the length of the curve x equals 1/3 square root of y times 1 minus 3 on the interval from 1 to 4. Oops. All right, so setting this up, I'll do this one with you because there's a bunch of algebra that's going to come into play. We're going to find the length of this curve. So what we're looking for then is the integral from 1 to 4 of the square root of 1 plus the derivative as a function of y, the derivative of this equation squared, and then dy. All right, so let's do a little bit of work here. Let's find the derivative of that function. X prime. Actually, I'm going to rewrite x first. I'm going to rewrite x first and distribute that 1/3 square root of y in. It's going to make it a little bit easier to work with. So I will just say this is 1/3 y to the 3/2 minus y to the 1/2. Now I'll find the derivative. Multiply 1/3 times 3/2 gives me 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. And I know I normally make you rewrite that, but for right now I'm going to leave it that way because we need to square this thing still. So I'm going to leave it like this before I square it. So let's square the derivative. I'm going to actually give you a minute to multiply these two together. So why don't you pause right now and go practice multiplying these together. Come back in a second. All right, I hope you actually did that. So we're going to find the derivative, multiply these two together. So let's do some algebra. 1/2 y to the half times 1/2 y to the half. 1/2 times 1/2 is 1/4. But then when I multiply y to the 1/2 times y to the 1/2, I add the exponents. So that just gives me just plain old y. Now if I multiply the outer 1/2 y to the 1/2 minus 1/2 y to the negative 1/2, that's a mouthful. The 1/2 times negative 1/2 is negative 1/4. Y to the 1/2 times y to the negative 1/2, that's y to the 0, or just 1. And then same if I multiply the inner two terms together. And then finally, negative 1/2 y to the negative 1/2 times negative 1/2 y to the negative 1/2, that's positive 1/4. And then add those exponents as y to the negative 1. All right, simplifying this derivative then, I end up with 1/4 y minus 1/2 plus 1/4 y to the negative 1. I'm going to leave it like that because there's a pattern that we need to look at. So let's put this back in. I want to just show you a pattern. I want to put this back in now to the formula that we have. The arc length is 1 plus the derivative squared. So it's 1 plus all of this. Now what's really, really, really important to remember is that this stuff in this parentheses was a result of squaring this. Okay, that was what all of that in the parentheses did for us. So let's now simplify what's under this radical, because somehow we're going to have to find the antiderivative of this. And with that radical, things just look really scary. So let's simplify what's under the radical. I can do 1 plus that in all that stuff in parentheses. So I've got some like terms. I can add this 1 and this negative 1/2 together. And when I do that, I end up with this. 1 minus 1/2 is positive. The reason I wanted you to notice that pattern is that now, because finding the antiderivative of this radical is really crazy difficult. If I let u equal the part under that radical, this is definitely not a u substitution problem because I don't see du in this thing anywhere. But what I do notice is that this is almost exactly the same as this. And I know that this came from that being squared. So in other words, what I'm trying to get at is that this new thing that we've just created can be factored. I want you to think about what it might be able to factor to. I'm going to give you a minute. All right. Basically, these are the exact same expression. This one, this new thing that we got, is almost exactly the same as what we started with here. The only difference is that it's plus 1/2 instead of minus, so that means everything is addition. So that means this part under the radical factors out to be 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 quantity squared. Now things are way more convenient because if I take the square root of this thing being squared, the radical goes away. So I end up with just 1/2 y to the negative, or 1/2, sorry, positive. And now what this means is I can just use the power rule. That's also another reason why I left it in that negative exponent in exponent form instead of making it into a fraction, because I knew it was going to get here again. So now finding the antiderivative is pretty straightforward. Add 1 to this first exponent, so that's y to the 3/2. 1/2 times 2/3 is 1/3. And then if I add 1 to this, that's 1 positive 1/2. 1/2 divided by 1/2 is 1. And then if I evaluate that from 1 to 4, remember you can do this without a calculator, and I would expect you to do this without a calculator. 4 to the 3/2 is the same thing as saying the square root of 4 cubed. And then similarly, well, this one's easy because it's just 4 to the 1/2, which is just the square root of 4. Okay, and then minus, let's plug 1 into this. Now this one's not bad because it doesn't matter what the exponent is. Okay, let's see. Square root of 4 is 2. 2 cubed 8, 8/3 plus 2 minus 1 to the 3/2 is 1 times 1/3 is 1/3. And then this is just 1. And then if you combine those, 8/3 minus 1/3 is 7/3. 2 minus 1 is 1. If you wanted to combine those, you could, but you didn't have to. That's the length. 10/3 units. And if I told you units, you would just put units, but it's 10/3 units long. That's how long that curve is. Okay, I think that's enough. I'm not going to give you another example here. We'll do another example in class.